Hello everyone, welcome to this new video series on number theory. So this is the very first lecture of this series. The link to the entire playlist is there in the description. You can check that out. So let's start with today's topic of mathematical induction. So the principle of mathematical induction can be divided into two categories. The first is first principle of induction and the other one is second principle of induction. Okay, so let's get to know what's the basic difference between these two principles of induction, and then we will be solving problems using both the principles. So coming to the first principle of induction, the statement says that if I have a mathematical statement which is denoted by Pn, and the statement is about natural numbers n. So first of all, the statement has to be true when n value is 1. So for n value 1, the statement has to be true. Now, if we assume that the mth statement is true, where m is any natural number, if the mth statement is true, under this assumption, if we can show that the m plus 1th statement is also true, then we can conclude that our mathematical statement Pn is true for all the natural numbers. Okay, so it has to be true for n value 1, and secondly, if for any mth natural number, if the statement is true, then under that assumption, if the m plus 1th statement is also true, then we can conclude that our mathematical statement is true for every natural number. So let's take a look at a few problems. This is the question that we have. It's saying that use mathematical induction to prove that the sum of n odd integers is n square for any positive integer n. So let's frame our mathematical statement. Let's say that Pn is the mathematical statement which says that the sum of n odd integers is n square. So that would mean sum of n odd integers is 1 plus 3 plus 5 plus, like this. If we go on, I'm taking the sum of all the odd integers. I have to take n number of odd integers, so that means I'll be reaching 2n minus 1. So if I count, this is my first integer, odd integer, second odd integer, third odd integer, and like this, if it goes on, then this is my nth odd integer. So I've taken the sum of n odd integers, and I have to prove that this sum is n squared. Okay, so this is our mathematical statement, and I have to prove this for every positive integer n, that means for every natural number n. So let's get started with our first principle of induction. We have to show that this statement is true for n value 1. So if I take n value 1, that would mean I'm just taking the first term of the series. So the first term of this series is 1. And if I put n value 1 on the right hand side, that would give me 1 squared. And from the left hand side, I'm getting a 1. So obviously both are equal. 1 equals 1 squared. Okay, so we're going to write this in this way, that P of 1, the LHS, P of 1, the LHS is giving me the first term of the series, which is 1, and the RHS, the right hand side, that's going to give me n squared, where n value is 1. So that would be P of 1 would be 1 squared, that's 1. So we can see that the statement is true for n value 1. So LHS is equals to RHS. Okay, so now we are going to assume that this statement holds for some randomly chosen natural number m, and with the help of that assumption, we are going to prove it for m plus 1. So let's say that let P n holds for some m belongs to natural numbers. So that means our statement is true for a randomly chosen natural number m. So that would give me my mth statement would be 1 plus 3 plus 5 plus. If I go on like this up till my mth integer, I would get 2m minus 1, and since I'm assuming this to be true, so it should give me m squared, right? So I am assuming that this is happening. Now under this assumption, I'm going to try to prove that the m plus 1th statement is also true. So now let's think, what are we trying to prove? Here we are trying to prove that if I take one extra term of the series, so I'm already taking the previously written terms. So these are the terms that I have written right from here. Now I need one more extra term because I want to write m plus 1th term. So the next term, the next odd integer after 2m plus 1, that should be, after 2m minus 1 should be 2m plus 1, right? And I'm trying to prove that my RHS should be, instead of m squared, I should be getting m plus 1 squared, because right now I'm having my m plus 1th statement. So if my mth statement is m squared, my m plus 1th statement should be m plus 1 squared. So now I am expecting to get the sum of this series to be m plus 1 squared, and if I get that, then I can say that my principle of induction has been established. Okay, so I'll try to manually do the summation of this entire series that I have. So it looks like a pretty easy arithmetic progression, right? This substitution, I already know that the sum of these terms is m squared, as I already have that from my mth statement, so I can just utilize that. So if I utilize that, I'll be getting m squared plus 2m plus 1, and that would be m squared plus 2m plus 1, and that's obviously the formula for m plus 1 whole squared, right? So we have done this with the help of the mth statement. We have proved our m plus 1th statement. Now if we use the arithmetic progression formula, then we could have also shown the same thing without utilizing the previous line actually. Okay, so that's not our concern. So we can say that therefore Pm plus 1 is true whenever Pm is true, right? So from the first principle of induction, we can finally conclude that hence our mathematical statement Pn is true for all natural numbers n, and this has been established using the first principle of induction. Okay, so now let's take a look at another problem. So this question is saying that using principle of induction, we need to prove that this mathematical formation is divisible by 24 for every natural number n. Okay, so let's formulate our mathematical statement. So our nth statement is trying to say that 2 times 7 to the power n plus 3 times 5 to the power n minus 5 is divisible by 4. Okay, so is divisible by 24, sorry, is divisible by 24. Now I don't want to write a statement inside our mathematical formation. Statement in the sense, I don't want to write these words that this expression is divisible by 24. I don't want words in it. I want an equation. Okay, if it's an equation, then that's something easier to prove. All right, so if I say that A is divisible by B, and I want to convert this into an equation, a nice looking equation. So if something is divisible by something, that means we are dividing by B. So when B is multiplied with some integer, let's say the integer is k, then I'm supposed to be getting my A value, right? So if B is multiplied with an integer, it gives me the value A. That actually means that A is divisible by B. All right, so the important thing is k must be an integer. Okay, this k must be an integer. The same thing, the same concept I want to apply over here. So imagine this is your A and imagine this is your B. So I have A is divisible by B. So I can write that my Pn statement is actually 24 times some integer, let's say k, is 2 times 7 to the power n plus 3 times 5 to the power n minus 5. Okay, so I've converted my statement into a mathematical equation. Okay, now let's get started with our induction process. So p of 1, if I put n value 1 right over here, then I will be getting 2 times 7 to the power 1 plus 3 times 5 to the power 1 minus 5, and that would be 14 plus 15 minus 5, and that would be 14 plus 10, so that's 24, and obviously it's divisible by 24. All right, so that's divisible by 24, right? So our n equals 1 statement is true. So now let's move on to our mth statement, which we're going to take under assumption. So let Pm be the statement. So I'll just copy paste the same thing, the same line that I've written, just instead of writing n, I'll be writing m, the same thing. It's 24 times. So if I'm writing with a different integer or a different natural number m, what I'm trying to say is that this right hand side value, instead of writing n, I'm writing m. So 2 times 7 to the power m plus 3 times 5 to the power n minus 5. Since I changed the value from n to some fixed value m, so obviously my multiplier should also change, right? Because this k multiplier was in correspondence with the value n. So if I change the value n to some other natural number m, so my multiplier should also change. So we will not keep it the same alphabet. Let's change it over to, let's say, q. All right, where again q has to be some integer. Okay, where q must be some integer. Okay, so this is something that I have taken under assumption. Now I'm going to try to prove the m plus 1th statement with the help of this statement. Okay, so now the m plus 1th statement, that's going to be, if I want to write the left hand side of it, it should be 2 times 7 to the power m plus 1 plus 3 times 5 to the power m plus 1 minus 5. Now I'm trying to show that this must be divisible by 24. So let's keep this in our mind, that what are we trying to show? We are trying to show this is divisible by 24. So if something is divisible by 24, that means this must be equals to 24 times some integer, right? 24 times some integer, not the exact same q integer again. It can change, or it should change actually. So let's call it p this time. So this is something that we are trying to show. Okay, so remember it, this is something that we are trying to show. This is equal to 24 times some integer. It can be any integer. All right, so now let's forget about this thing and let's get started with our manipulation. So we need to do some substitution from our previous line. Okay, so what can I substitute? Let's see, I can break 7 to the power m plus 1 in this manner. 2 into 7 to the power m. So I've broken up 1 from the power and brought it in the front. Okay, and the remaining things, let me just keep them as it is. 3 times 5 to the power m plus 1 minus 5. Now the reason for doing this is that I can substitute the value 2 times 7 to the power m right from here. So this value I can just substitute it. 2 times 7 to the power m, I'll get the value from the previous line by sending off these two terms to the left side. Okay, so I'll send off these two terms to the left side, and the value of 2 into 7 to the power m, I'll substitute that over here. So I already have a 7, and if I take these terms on this side, so I'll be having 24q, this one bring it to the left side, minus 3 into 5 to the power m, minus 5 to the left side, plus 5, and the remaining terms as it is. Okay, so remember, we are trying to bring out a 24 common of the entire expression and get an integer remaining inside. So wherever you find 24, let's try to bring that out common. So I can see a 24 right over here. So if I take that common, I should be having 7q. All right, then multiplying 7 with all the terms that are inside, so minus 21 times 5 to the power m, 7 into 5 plus 35 plus 3 into 5 to the power, okay, since I have a 5 to the power m here, so I would like to break this down as well. So I can make this 15 times 5 to the power m minus 5. Okay, so I'll just regroup the terms, the similar terms, I'll just regroup them. So 21 times 5 to the power m and 15 times 5 to the power n, minus and a plus, so that would give me minus 6 times 5 to the power m, 35 minus 5, and that would give me a plus 30. Okay, so from here I need to bring out a 24 common. So these two are the problematic terms. Over here I've already got a 24. So what I can do is that I can break up this 30 into 24 and a 6. Okay, 24 is my required term, right? So I can take this 24 and that 24 common. So if I take the 24 common, I have 7q plus 1, and the terms remaining are 6 into 5 to the power m and this 6. Okay, so now I can take the 6 common. So 24 times 7q plus 1, if I take a minus 6 common, or let's say I'm taking a plus 6 common, that would give me 1 minus 5 to the power m. Now you might be stuck right over here thinking, how can I take a 24 common out of this? As you can see, you're not getting a 24 right here. So now if we need some algebraic expansions here, I need you to recollect this formula specifically, 1 minus x to the power m. Alright, this is the formula that you need to remember. The factorization of this formula was 1 minus x times x to the power m minus 1 plus x to the power m minus 2, and all the way down up till 1. So this was the simplification of 1 minus x to the power m. Now you can visualize your 1 minus x to the power m right over here, and you can use this entire simplification to this particular part, 1 minus 5 to the power m. So let's just do that. I will move this to the side for your reference, and I will continue my process. So 24, 7q plus 1 plus 6 times. Okay, so 1 minus x to the power m, I will have a 1 minus x factor, right? A 1 minus x factor, that would be a 1 minus 5 times, I will have x to the power m minus 1, which is 5 to the power m minus 1 plus 5 to the power m minus 2, all the way down up till 1, right? So now you can see I have got 1 into 4, and that's my 24 which I was looking for. Okay, so 24 times 7q plus 1 plus 24 times 5m minus 1 plus 5 to the power m minus 2 plus all the way down till 1, right? So now I can take an entire 24 common. I will be having 7q plus 1 plus 5 to the power m minus 1, 5 to the power m minus 2, all the way down up till 1. Now you don't need to simplify this entire thing. As you can see, each term of this series is an integer, right? 7q, now remember your q was an integer, so 7q is also an integer, 1 is an integer, m was a natural number, so 5 to the power m minus 1, that's also an integer, this is also an integer, all the way down up till 1, everything is an integer. So the sum of all integers is again an integer, right? So I can use that concept and I can say that 24 times, let's call this entire thing as a p, where I can say that p is definitely an integer. Now remember, this is what we were trying to show. We were trying to show that our pm plus 1, whatever was the statement, is divisible by 24, so that means is equals to 24 times some integer, and we have got exactly that. Our pm plus 1 is 24 times an integer, which would mean that pm plus 1 is true whenever Pm is true, because I took the help of the mth statement in order to prove the m plus 1th statement. So therefore, by induction, or I should be more specific actually over here, by first principle of induction, Pn is true for all n belongs to natural numbers. Okay, so this is how we go through the problems of induction. Let's take a look at a little bit different kind of a problem. We have to prove that 2 to the power n is less than n factorial for all natural numbers n greater than equals to 4. Now this might be a little bit different compared to the problems that we were doing just now. Here I don't have to show that the statement is true for n equals 1, because it's already mentioned in the question that the statement is true when n is greater or equals 4. When n is less than 4, it's definitely not true, and you can just check that out. Let's say if you take n value 1, you can see the left side would be 2 to the power 1 and the right side would be 1 factorial, so 2 less than 1, that's obviously not true. Okay, so the statement is obviously not true up till n value 3. It starts becoming true for n equals 4 and greater. Okay, so now you might think that how can I do this by induction, because the induction statement clearly mentions that your statement has to be true for n value 1, which was the very first requirement. So we can actually work around that. We can reframe our statement by saying that let Pn be the statement such that 2 to the power n less than n factorial. Now if I tell this, then I can say that n value 1 is definitely not satisfied. So what I can do, I can just change it in this way. I can write n plus 3 is less than n plus 3 factorial. Okay, so if I reframe my question, now see, if you put n value 1, if you put n value 1 right over here, so that becomes 2 to the power 4, and if you put n value 1 over here, that becomes a 4 factorial. So that means the same statement I am showing for n value 4, but I have showed that by taking n value 1 by manipulating my statement. Okay, so when we are manipulating in this way, it is better not to write the same alphabet that's mentioned in the question. Here the alphabet is n, which is the generalized term of the question. So instead of that, let's say our statement is m state, or let's say our statement is given by pk such that 2 to the power k plus 3 is less than k plus 3 factorial. So if we are able to prove this mathematical statement, then it would be same as saying if we are able to prove this for all k belongs to natural numbers, that means starting right from 1, because if you put n value 1, you basically get the original question with n value 4. If you put k value as 2, so if you put k value 1, you are actually doing the original question for n value 4. If you take k value 2, you are doing the original question corresponding to n value 5, and so on. So if you are able to prove the statement pk to be true, then obviously you are proving the original question to be true. Okay, so it's just a way of manipulating the statement. All right, so we are taking this as our problem and we're going to prove this. Okay, so for k value 1, P1 would be 2 to the power 1 plus 3 less than 1 plus 3 factorial. So that would mean 2 to the power 4 less than 4 factorial. That would mean 16 less than 24. And that's definitely true. Okay, so which is true. Right, so for n, or for k equals 1, we have proved our statement. So now let's say that let Pm be true for some m belongs to natural numbers. So I will just reframe the statement, just write the same statement actually. Instead of writing k, I'll take m. Okay, so my mth statement would be 2 to the power m plus 3 less than m plus 3 factorial. Okay, now with the help of this statement I need to prove that my mth statement is also true. Okay, so now p m plus 1, that would be 2 to the power m plus 1 plus 3, right? I've taken the m plus 1 right over here and the plus 3 along with it. Now remember, what are we trying to show? Remember that we are trying to show that this is less than, we are just replacing the m with the m plus 1. So if I replace this m with the m plus 1, so we are trying to show m plus 1 plus 3 whole factorial. Okay, so we are trying to show that this is less than basically m plus 4 factorial written in this format. Okay, so keep this in your mind. Alright, so we are going to start from here and slowly we are going to show that it is ultimately less than m plus 4 factorial. Alright, but we will need the help of the previous line. Okay, now to get the help of previous line, you can see you have a power of m plus 3 and over here you have a power of m plus 4. So I need to get rid of one power. So I can write this as 2 times 2 to the power m plus 3. Now I can get this value substituted right from here. So I have 2 to the power m plus 4. If I substitute this value, then I have the inequality less than sign. So this is ultimately again less than 2 times, instead of 2m plus 3, I can write m plus 3 factorial. 2 times m plus 3 factorial. So I have 2m plus 4 is less than 2 times m plus 3 factorial. Okay. Now, what is the minimum value of m here? See, the minimum value of m can be 1 because m belongs to natural numbers, right? So the minimum value of m can be 1. Okay, so can I say that m plus 4 is definitely greater than 2? Or I'll just write the 2 this side. 2 is definitely smaller than m plus 4 because the minimum value of m can be 1. Even if m is 1, then the right side is still bigger. So for any natural number m I take, this statement is always true. Now you might think, why am I saying this? Because this 2 is just over here. Okay, so we can replace this 2 with a m plus 4 sign followed with a less than sign inequality. So I can say that this entire thing is even further less than, instead of 2 I'm taking m plus 4 and I already have a m plus 3 factorial along with it, right? So I replace the 2 with the m plus 4 using this inequality. Alright, so 2 to the power m plus 4 is less than, now if I take this multiplication, m plus 4 multiplied with a m plus 3 factorial, that would give me a m plus 4 factorial. Now just recollect, as I was telling you, this is what we were trying to show, right? If I break this down, I should write it in this format. M plus 1 plus 3 is less than m plus 1 plus 3 factorial. So this m plus 1 and this m plus 1 tells us that this is our state m plus 1th statement, right? So we have shown that the m plus 1th statement is true whenever the mth statement is true. So our conclusion follows that therefore Pm plus 1 holds whenever Pm is true. So therefore, by first principle of induction, Pk is true for all k belongs to integers. Remember, we had manipulated our statement. Instead of Pn, we had made it Pk. So now again, this is further equivalent to saying that the original question is true for all n greater or equals 4, because k was actually bumped up with a plus 3, right? We had actually increased the value with a plus 3. So if the kth statement is true, then that means the original question is true where n is greater or equals 4. Okay, so that's what we have proved using induction. Okay, now let's see what is the difference between the first principle of induction and the second principle of induction, and how the problems are going to be different. Okay, now coming to second principle of induction, it's almost kind of same but with a little bit of difference. So here it's saying that Pn be the mathematical statement about natural numbers. So our first criteria is the same as before for the first principle, where P1 has to be true. So up till here everything is all the same as first principle. The change starts at the second point. Here it is saying that Pm is true whenever, now remember, if Pm is true whenever, in the first principle it should have been whenever the previous statement is true, right? Or we were actually saying that Pm plus 1 is true whenever Pm is true. So that's equivalent to saying that Pm is true whenever Pm minus 1 is true. That was our first principle. But here it is saying that whenever Pk is true for all k less than m. So in short, this means that this point is same as saying whenever Pm minus 1, Pm minus 2, so on up till P1, when all these are true, or I would say that Pm is true whenever all these statements are true. Okay, so in first principle, what was the requirement? The requirement was that Pm is true whenever Pm minus 1 is true. Up till here was our first principle. But if this is not enough, sometimes only the previous statement is not enough to prove the next statement. Okay, sometimes we require all the previous statements or at least some of them. Okay, so when we require more than one previous statement, then that is called second principle of induction. Okay, so this will be necessary in questions where the m minus 1th statement is not enough to prove the validity of the mth statement. You will require more than one statement, more than one of the previous statements to prove the validity of your mth statement. Okay, so let's take a look at a problem. So this is saying using mathematical induction, prove that this expression is always an even integer. Okay, so this pretty much looks like a question of first principle induction, but when I start solving, you will see that just the previous statement won't be enough to prove the next statement. You will require even more number of statements from the previous steps. Okay, so let's get started in the usual manner. Let's make a mathematical statement out of this, that this is an even integer. Now again, I don't want words in my statement. Okay, I want it in form of an equation, right? So if something is an even integer, then the equation form of it should be that it's a multiple of 2, right? An even integer is always a multiple of 2. So I can say that my nth statement is 3 plus root 2n plus 3 minus root 2 to the power n. That's a multiple of 2. That means 2 to the power some integer k. Okay, 2 to the power some integer k. So that ensures that it's an even integer. Okay, so let's get started with n value 1. So p of 1 would give me 3 plus root 2 to the power 1 plus 3 minus root 2 to the power 1, and my root 2 would get cancelled. That would be 6, and 6 is definitely an even integer, right? Which is an even integer. So our first statement is true. Okay, now let me assume that starting from n value 1 up till m minus 1, all statements are true. Okay, so I'm saying that I have already proved for n value 2, so let p m minus 1, p m minus 2, and so on all the way up till the second statement, because first one is already proved, are true. Okay, so I am taking this under an assumption. Now with the help of these statements, I want to prove that the next statement, that is the mth statement, is true. Okay, Alright, now I'll just, for your reference, I will write what these actually mean. Now the m minus 1 statement would actually mean that 3 plus root 2 to the power n minus 1, m minus 1 should, sorry, m minus 1 plus 3 minus root 2 to the power m minus 1 is an even integer, let's say 2 times k1. Similarly, p of m minus 1 should be 3 plus root 2 to the power m minus 2 plus 3 minus root 2 to the power m minus 2 is equals to, again, some integer, let's say 2 times k2, some even integer k 2k2, where k2 is some random integer, and so on. Okay, so I'm writing this just for your benefit so that I can take the reference of these equations. Okay, so now I'm starting with the mth statement. Okay, so the mth statement would be 3 plus root 2 to the power m plus 3 minus root 2 to the power m. Now just for a better visualization, let's say that let me call 3 plus root 2 as x and 3 minus root 2 as y. So this will just help me to do my algebraic simplifications. So this is x to the power n, sorry, x to the power m, and this is y to the power m. Okay, now I'll do one algebraic manipulation. I want to write this statement in this format: x plus y whole into x to the power m minus 1 plus y to the power m minus 1, and plus minus whatever terms are needed for the adjustment. Okay, now what I will do, I'll first break this multiplication and see what are the total terms. Whichever term is missing, I'll fill that up in this step. Okay, so first let me concentrate on this multiplication. Whatever extra terms I'm getting, I'll come back to this line and I will complete it. Okay, so if I do this multiplication, I'll be getting x to the power m, then the x multiplied with the y term, that would be x y to the power m minus 1, y with the x term, that would be y to the power y into x to the power m minus 1, y with the y term, that would be y to the power m. Okay, now see, the original question had x, or the original line had x to the power m, y to the power m. Those two terms are already present over here, and these are basically the extra terms, right? These are the extra terms if I write it in this fashion. So that means I need to get rid of these extra terms. So I need to write a minus of xy to the power m minus 1 minus yx to the power m minus 1. Okay, so now think, if you write this line, then I have these two terms remaining. I have just taken the multiplication here, and these two terms are remaining. So xy to the power m minus 1 minus yx to the power m minus 1, right? And so these terms are supposed to get cancelled, and you are remaining with x to the power m, y to the power m, which was my actual line. Okay, so I'll just get rid of this now. This was just for your understanding. So I have written this expression in this format. Now what is the benefit of this? Let's see what's the benefit we can get out of this. Let's see how much can I take common from these two terms. I can take the product xy common from here. So if I take the product xy common, I should be having x to the power m minus 1 plus y to the power m minus 1. Okay, now recollect that this was my m minus 1th statement, x to the power m minus 1 plus y to the power m minus 1. This was my m minus 2th statement. This was my m minus 1th statement, and did I write that correctly? Sorry, I think I have done a little bit mistake here. If I take x and y common, I should be having x to the power m minus 2 and y to the power m minus 2. Okay, sorry for that miscalculation. So I can see that the m minus 2th statement is present over here, and the m minus 1th statement is present over here. So as you can see, I require the m minus 2th statement. Just the m minus 1th statement is not being sufficient here. Okay, in the first principle of induction, only the m minus 1th statement would have been sufficient, but here I am requiring another statement, which is the m minus 2th statement. Maybe in some other question we would require even another statement, which would be p m minus 3 and so on. Okay, so you can require all the previous statements or maybe some of them for doing your proof of the mth statement. Okay, now we have two more terms, which is x plus y and x into y. Now this was our assumption, so x into y would be the product of this two would be a square minus b square formula. So a square minus b square, so 9 minus 2, so that would be a 7. So x into y is 7, and again I have a x plus y. My x plus y, if I take the addition of these two, then I would be getting 6, right? So I'll just take the help of the addition and the multiplication and put them over here. So I have 6 times, this is my m minus 1th statement, and as per the m minus 1th statement, this value is equals 2 into k1. So this is 2 times k1 minus x into y is 6. This is my m minus 2th statement, which is 2k2. So 2 times k2, where k1 and k2 were supposed to be any integer. Okay, so now I can see I can take an entire 2 common because I want to prove that this is an even number. So if I take an entire 2 common, I'm left with 6k1 minus 6k2, and obviously 6k1 minus 6k2, obviously this is some integer, right? Because k1 and k2 are integers, so this entire thing should be some integer. So I can call this, let's say, 2q, where q belongs to integer, and since it's of the form 2 times an integer, so obviously it's an even integer. So I have, therefore, pm plus 1 is true whenever here I have shown pm is true. Pm is true whenever pm minus 1 and pm minus 2 is true, right? So I took the help of the previous two statements. So therefore, by second principle of induction, Pn is true for all n belonging to natural numbers. So this is all about mathematical induction. Now we will move on to the next video in lecture 2, and the link of the entire playlist is given in the description of this video. Thank you for watching. See you again in the next video.